Let's talk about conditional probability. Pretty simple concept. It's basically the probability of something occurring given that something else occurred first that it depends on. Good real world example is if you go to Amazon.com and look at the feature that's like people who bought this also bought, or people who viewed this also viewed. You can think of that in terms of conditional probability. What are the odds of purchasing another item given that you purchased this other item first? Same concept. Now, the notation in conditional probability is probably the most confusing part. So we're going to try to walk you through it in this lecture, but it would help if you grabbed an extra cup of coffee or put on your thinking cap, whatever it takes to get yourself into your sharpest mental state, because this is one of the more challenging things to get through. With that, let's dive in, and I'll try to make it as simple as possible. Let's talk about conditional probability. Again, simple concept, but the notation can trip you up sometimes. So let's just dive into what that notation is and what it means. Now, the basic concept of conditional probability is that if I have two events that depend on each other, I can make a statement about the probability of that second event occurring given that the first event occurred. Now, the notation that we're going to use here is twofold. There's P, A, comma, B, and that means the probability of both A and B occurring independently of each other. And then we have P of B bar A, that's the probability of B given that A has occurred. So that implies some dependency between B and A. And we can tie this all together using this handy-dandy equation here, where the probability of B given A, that is the conditional probability of B given event A, is equal to the probability of A and B together divided by the probability of A. So you can use that to tease out the conditional, the dependence between B and A. It'll make more sense with a real example, so let's take a look at a real example. Let's say that I give my students two tests, and overall 60% of my students passed both tests. So if we call the tests A and B, PA comma B would be 60%. However, the first test was easier. 80% of my students passed that one. So if B is the second test and A is the first test, P of A would be 80% in this example, right? You can see this gets confusing pretty quickly with all the A's and B's and commas and pipes, but let's review again. So 60% of the students passed both tests, so P of A comma B is 60%. The first test was easier, 80% passed that test, so P of A is 80%. So now how do I figure out the percentage of students who passed the first test who also passed the second? So what's the probability of passing my second test given that you passed the first test? That's conditional probability. So we're asking for the probability of B bar A, the conditional probability of passing test 2, given that you passed test 1. And we can compute that using the equation that we just saw. P of B bar A, the conditional probability of B given A, is equal to the non-conditional probability, P A comma B, which was 60%, over the probability of A, which is 80%. And if we do that division, we end up with 75%, and we can say that 75% is the conditional probability of passing the second test, given that you passed the first one. Make sense? Hit pause and digest this for a minute, because with all these letters and different punctuation marks and whatnot, it can get confusing. So let me just dive you into a notebook and we'll go through a bunch of other examples to try to make this notation and how to handle all these things second nature to you. And when we're done, I'll give you a little bit of an exercise so you can go and practice it yourself. Okay, for this exercise, I want you to open up the Conditional Probability Exercise notebook in your course materials. And I'll try to walk through this a little bit slowly. This is sort of a tough thing to wrap your head around a little bit. What we're going to do in this activity is generate 100,000 random people, and let's say that they're all customers on a big e-commerce website like Amazon or something. For each of these 100,000 people, we'll randomly assign them to a given age range, being in their 20s or their 30s or their 40s, all the way up to their 70s. And we're going to create a conditional probability, a dependence between their likelihood of purchasing something and their age. Basically, we're going to say that the older you are, the more likely you are to buy something. So if you're young, you'll have a lower probability of purchasing something. So let's say that we say the probability of purchasing something is called E, and the probability of actually being in a given age range is F. That means that we're going to have a dependency, a conditional probability between E and F. All right, so let's walk through the code here that sets up that random data set. I get a lot of questions from people about how this code works, so bear with me, guys, if you do know Python already, but for the people that are new to it, this does take some explaining, so I'm going to go through this line by line. All right, so we're going to start off by importing random from the NumPy package. Nothing exciting there. That's just so we can actually generate random numbers within this little snippet of code here. Random.seed just generates a seed value for the random number generator. The purpose of this line is to make sure that we get consistent results every time we run this code. So as before, we used to get different results every time you ran this, but by having a consistent seed number, That means that we'll get the same results back for our random numbers each time that we run this. The number 0 is arbitrary. All that matters is that it's the same value being used each time. It could be 1, 2, 3, 4, or any number you want, as long as it's the same one. That's all that's going on there. We're just making sure we have some consistency in our results. Next, I'm setting up 2 Python dictionaries called totals and purchases. And what this is doing is keeping track of how many total people I have in each age range, the 20-year-olds, the 30-year-olds, the 40-year-olds, and so forth, and how many purchases were made by each person in those age ranges. So basically I'm saying initially I have 0 people in the 20-year-old bucket, 0 in the 30-year-old bucket, and 0 in the 40-year-old bucket, and so on and so forth. And I have 0 purchases from 20-year-olds, 0 purchases from 30-year-olds, 0 purchases from 40-year-olds, and so on and so forth. So this is just how I'm going to keep track of the total number of people and the total number of purchases associated with each age group. I will also keep track of the total number of purchases regardless of age with the total purchases variable. Next, we're going to create a loop to iterate through 100,000 random people that we're going to create. And that underscore is just a placeholder. I could just say for x in range 100,000 or whatever you want. But since I'm not actually using that value anywhere within the loop here, I can just use the underscore character as a placeholder. It just means I don't really care what that value actually is each time through. I don't care that this is user number 1776. I can just discard that information. That's all the underscore means. It means I don't really care what the actual number is. So for each of these 100,000 people, we're going to iterate through this loop 100,000 times. And for each time, we will assign a age decade to this person. Random.choice will just randomly pick a value out of this list that we pass in. So it will randomly pick one of these numbers, 20, 30, 40, 50, 60, or 70, evenly distributed. So we will have a random even chance of being a 20-year-old or a 30-year-old or a 40-year-old, all the way up to a 70-year-old for each individual person. Now here's where things get a little bit weird. Based on your age, we compute a purchase probability. So we're taking your age and dividing it by 100 to figure out the odds of you actually purchasing something from our website. So for example, if I'm in my 20s, I will take 20 divided by 100. That works out to 0.2 or 20%. So 20-year-olds will have a 20% chance of actually buying something. 30-year-olds will have a 30% chance of buying something, and so on and so forth. So this is how we're figuring out that younger people are less likely to buy something than older people in our randomly generated data set here. As we go through it, we'll bump up the total for that age decade by 1, meaning that we've generated a new random person within this age range. And here we're saying if random.random is less than that purchase probability, to actually attribute a purchase to this person. How does that work? Well, random.random just randomly selects a value between 0 and 1. So if that random number is less than our purchase probability, we say this person actually bought something. Let's look at an example to make that a little bit more intuitive. Let's say that we have a 30-year-old. Okay, so if someone's in their 30s, their purchase probability will work out to 0.3 or 30%. So if our random number between 0 and 1 comes out to be less than 0.3, that person is attributed to a purchase. If it's greater than 0.3, they did not buy something. So you see how that works? It's how we're basically rolling the dice to see if this person bought something or not, given their overall probability of purchase for their age range. So as we're done, we're building up these total number of purchases that are done across the entire data set. We're also keeping track of purchases for that individual age decade, and we're also keeping track of the total number of people in each age decade as well. We'll need all these numbers to figure out things like P of E and P of F and P of E given F and all that stuff. So let's go ahead and run this. And that generates our fake data set that has a dependence between age and purchases. So let's take a look at what we got. I would expect the totals for each age range to be roughly consistent, and they are. So we have about 16,500 people in each age decade. So that's good, a nice even distribution. That's what we expect. But if we look at the purchases attributed to each age range, you can see that that is increasing based on age. So we have that dependency that we tried to model in there working nicely. So about 3,000 20-year-olds purchased something, but about almost 12,000 70-year-olds bought something, even though that they were evenly distributed in number of people. So we're seeing here very clearly that there is a relationship between your age and your likelihood of purchasing something. Okay, so we have a nice little fake data set to work with here for conditional probability. We can also compute the total number of purchases across the entire data set. That comes out to 45,012. And now we have the values we need to work with for playing with conditional probability. Okay, so again, a lot of this is just getting your head around the notation and keeping track of what letter means what. So again, we're going to call E purchasing something and F a given age that you're in. So let's start by computing P of E given F. This is a conditional probability between making a purchase and F, where we're going to call that being in your 30s. We'll just arbitrarily select an age range there. So the probability of purchasing something, E, given that you're in your 30s, F, we can compute that directly, actually. We can just figure out how many 30-year-olds bought something as a percentage. So let's go ahead and just compute that. How many total purchases did we see from 30-somethings, and how many people were in that data set? And that works out to 0.299, almost 0.3, right? We can also independently compute P sub E and P sub F. P sub F will be the probability of being 30 overall in this data set. That's easy to compute. We'll just take the total number of 30-year-olds divided by the total number of people in our data set, and that works out to 16.6%, 0.166. P of E is just the overall probability of buying something regardless of your age, if there was no dependency there at all. So to compute P of E, we'll just take the total number of purchases across everybody regardless of age, divided by the total number of people overall, and that works out to 0.45 or 45%. So overall, in our entire data set, taking age out of the equation, there's a 45% chance of buying something. All right, so this is where you start to put on your thinking cap a little bit. So wrap your head around this statement. If E and F, that is buying something and your age, were independent, then you would expect P of E given F to be about the same as P of E, right? If there was no dependency between buying something and your age, you would expect the overall probability of buying something to be the same as the probability of buying something given your age, because there shouldn't be a dependency there. It shouldn't matter. F shouldn't matter. But we've seen that that's not true, right? So P of E we computed to be about 45%, but P of E given F we computed earlier to be about 30%, or 0.299, whatever it is. These numbers are fairly different. So that alone is telling us that E and F are dependent, that there is a condition between these two things. And we know that's the case in this example. We artificially created a dependency between purchase probability and age. So that's one way to tease that out of the data right there. If you see that P of E and P of E given F, or if you want to use different letters you can, P of A is not equal to P of A given B, whatever letters you want to use, it's just notation. If those aren't the same, then there might be a dependency going on there that you need to know about. All right, let's also compute P of E comma F. Again, this is all about notation. P of E comma F is different from P of E bar F. So P of E comma F is the overall probability of being both in your 30s and buying something without a dependency there. So we're looking at the overall probability of being both in your 30s and buying something, not just restricting that to the population of people that are in their 30s. We can compute that easily enough. We can just look at the total number of purchases from 30-somethings over the total size of the data set here, and that works out to about 5%-ish, 0.049. While we're at it, we can also compute the product of PE and PF. That's just going to be multiplying PE and PF, the overall probability of buying something, and the overall probability of being in your 30s. That comes out to about 7.5%. Now, in statistics, when they talk about probability, you'll often see the relationship that P of E comma F is equal to the product of P and E and P of F. But that is only true if E and F are independent. Now, we found here that P of E comma F, the overall probability of just being in your 30s and buying something out of the total data set, is about 0.05. But P of E times P of F is about 0.075. So when you have a dependency going on between these two variables, there's a conditional probability going on. And the relationship of P of E comma F equals P of E times P of F no longer holds. So that's another way you can kind of figure out that maybe there's a dependency going on here that's messing up your results. However, we can go back and check that equation that we gave back in the slides and just see if P of E given F is in fact equal to P of E comma F over P of F. And that's just a way of computing conditional probability if you cannot compute it directly as we could in this example. And sure enough, we can prove that that is true. The probability of E comma F, that's just going to be the total number of purchases from 30-year-olds over the entire data set, over P of F, which we computed earlier. That does work out to 0.29929, which is exactly the same as P of E given F that we computed way up at the top of this, right? So let's double check that, 0.299295, same number that we got up here originally. So that's cool. The math works out. Wow. Okay, so this is basically a couple of ways to figure out if you have a dependency in your data that you might not have known about, and a way of computing conditional probability given other things that you might know. So anyway, let's do a little assignment here, a little bit of a challenge, if you will. So your task, should you choose to accept it, is to modify the code above such that the purchase probability does not vary with age. So remember up here in this first block up here, we had this purchase probability that was a function of your age. Just make that a constant value instead. See what that does to your results. So if you do that, can you generate a new data set where you can show that P of E given F is about the same as P of E? That would show you that there is no condition there. If you show that to be true, that P of E given F is the same as P of E, then there is not a dependency between those two things. And that's a mathematical way to find that. So give that a shot and see if you can prove that to yourself. And I'll show you my solution to that in the next lecture. So there you have some examples of using conditional probability. Again, the concept's not that hard. It's just really easy to get tripped up on all the notation with all the pipes and commas meaning different things and stuff. But once you get used to it, it's not so bad. So I hope you have a chance to dive into the homework assignment here and try this little exercise of playing with it yourself and removing that condition and confirming that conditional probability ends up wiping itself out in that case. Let me show you my solution in the next lecture.